Okay, hello everyone. So yeah, a bit of a double act this morning from myself and Ant, and we're answering the question, what's the problem with trunk mains leakage, and is it a real problem, which was posed to us. So I'm going to look at this from a flow monitoring perspective, and can we work out the size of the problem if we use flow monitoring and maths. And then Ant's going to talk about some of the practical survey methods to try and quantify the problem in our big pipes. And I think it's well, for as long as I've been working in the industry, and I think it still is the case, there are some people who will say trunk mains are not a problem, they don't leak. And I think hopefully by the end of my presentation and Ant's presentation, you might have decided that at least some pipes will definitely leak. Okay. So the upstream network, by this I mean trunk mains, but also often service reservoirs, is quite different to the pipes that we spend a lot of time talking about in distribution. So they are, they're big diameter often, often have long lengths without any connections. The big pipes also have big meters on them, distribution input meters, and then the sort of outlet from these big pipes, DMA meters. They have some directly connected customers. They might be large logged customers, but you might also have a few households just connected to a trunk main because that was the only pipe around, or it could be a legacy issue. They effectively have continuous flow coming through them. So unlike your DMAs where you'd hope that flows drop down, it would still be continuous, but they drop right down during the night. Actually, trunk mains often have flow all the time because they might be doing things like filling service reservoirs, etc. So the flow isn't so connected to our kind of daily patterns of use. Oh, and I've already said, yeah, large diameter pipes with different materials, different conditions. I'd say asset records on some of these big pipes are no better than the asset records on many of the other pipes we have. So we have to think about them a little bit differently to DMAs when we want to work out what's going on. And one of the reasons why people are slightly sceptical about the approach that I quite love, which is doing balances across them, is because of the meters. So I'm going to talk about that in a little bit more detail. But fundamentally, I believe if you can't measure it, you can't manage it. It's an very old saying that we've used time and time again. And I think it comes back to that water balance question of what is this unaccounted for water? And I personally believe if we can get the water in the right buckets and we know where it's going, then we can start to manage it. And if we don't know if a leak is in a DMA or in the trunk main network, how do we know where to send resource or how to manage out the problem from occurring? So I think we have to focus on quantifying, understanding the upstream leakage to make sure that we're spending the right amount of resource in the DMAs and in them. So to measure upstream leakage, you're going to need meters, big meters on these big pipes. So you need to have a good strategy to make sure that those meters are sized correctly, are put in the best locations to be able to break the upstream network down. And also to make use of existing meters and understand those meters. Do you actually know which asset is out there? Do you know what type of meter it is, when it was installed? Have you matched the serial number to the age that you think it is and actually checked that that makes sense? So asset records of large meters, DI meters everyone knows about. They have to be verified, that people know where they are, what they are. They might not be very good, but they know what they are. DMA meters sometimes have been fit and forgotten. Interstitial meters, that's a fancy word for ones in the middle of a network that aren't necessarily serving a real purpose. Often don't have a clue. You might know there's a meter in the ground, but no one really knows what it was or where it came from. So making sure the asset records are there is quite important as well. Once you've got all that metering in place and you've got good high quality data coming from them, then you can actually start to do upstream losses assessments, which in turn means you can define interventions, whether that's going out finding leaks, whether that's reducing uncertainty, whether that's working with customers to prevent surge in a network, whatever it might be, you can actually say this is the right intervention to do in the area. which in turn means that you can actually reduce leakage, do surveys, find leaks, fix leaks, repair leaks, move on. Okay, so the metering. So everyone says, well, actually, if you've got these big meters, they're going to have big uncertainties around them, and that uncertainty will be greater than the actual result of your balance in the first place, so what's the point? And I think it's a valid point, but there's a lot of insight out there to actually understand and make use of the uncertainty information about meters, verification records, and our understanding of meter performance to be able to manage that uncertainty and actually inform those intervention decisions off the back of it by using that understanding. So for anyone who's not familiar with metering, effectively you can't trust the number that the meter says on it. You have to make sure that you understand how accurate that number is before you use it. So meter uncertainty is influenced by lots and lots of different factors, including and not limited to age of meter, the actual technology that's being used, so whether it's electromagnetic or ultrasonic or a turbine meter, performance issues, so has it been stressed through its life or has it just had one sort of continuous flow going through it, and other influences. Is it installed appropriately? Has it got 90-degree bends immediately upstream, downstream of it? Is there lots of sediment in the water going through it causing additional wear? All sorts of other influences. But we can take that information and meter test records to actually estimate the systematic error from a meter, otherwise known as under and over registration. And then we can use the sample of all those meters that have been tested to actually estimate a confidence band around that error estimate. So you can end up working out how to adjust your flows to kind of get the most accurate idea of the real amount of water passing through the meter, and also understand how sure you are about that number. The pictures on the slide, I should just say, are of some big meters and also of a large meter sort of test rig, a flow loop that can be used to test them. So once we've got all this information, I forgot this slide is animated, we can then use the flow data from the meters, the uncertainty information about the meters, knowledge of the customers directly connected to a particular length of trunk main network, and also any contextual information, so asset information about the network, so is it steel pipes, is it cast iron pipes, is it all PE? Events data, is it in an area where there has historically been a lot of bursts, etc., to both create a flow balance that takes into account uncertainty and also to make the best intervention recommendations off the back of it. And so this is a kind of a dashboard presenting some results, and I'm going to run through a few different examples from across 3 different companies of different kind of elements of what you can find from doing these upstream balances, just to provide a bit of information. So I said at the start, it's not a DMA, so we're not only interested in the night use period, because actually, fundamentally, if the flows are lowest through some of the meters at night, that's when they're likely to be most uncertain. So we can actually get a lot of valuable information from looking at the daytime period when flows are higher. We can actually look at the diurnal profile that results from the balances, so the average of all the midnight points, all the 15-minute pass points, etc., to inform whether or not we might have got our uncertainty estimates correct, our meter under registration estimates correct, or whether there might be customers directly connected to the trunk main that the company isn't aware of. A housing estate that actually got connected to the trunk main and they thought was connected to the neighbouring DMA. And this does happen. This is not me making up kind of insights you can find. And so when you do this is quite a simple one, but you basically get your kind of losses estimate for the area and you get an uncertainty band around it. If that uncertainty band is sitting above the 0 point comfortably, and there's no major metering issue like one of the meters doesn't work, then you've probably got some sort of losses in the area, and that might be a loss going to a customer that you don't know about, or it could be a leak. And that's the importance of the uncertainty band. If your uncertainty band is crossing 0, then actually you might just want to get a better grip on your understanding your meters to be able to work out whether or not it's worth spending any further time there. And I think the clever bit is that this is more engineering than data science. There's a lot of data number crunching that goes to pulling everything together, but actually it's engineering insight that's used to say, well, what could actually be happening and causing this diurnal profile, or for this period of time a funny thing to occur, or if we think there is a loss in this area, which pipes in particular might be the kind of first port of call for looking for a problem. Is the cathodic protection working on that major steel pipeline? Who knows? The water company probably doesn't know. Second example here then of another was TDMA, as I call them, or tiles you might hear them as, or TMAs, or upstream area, or yeah, lots of different words are used. So this is just an example of a much wider uncertainty band, but you can actually see there's a rising pattern. So even if the real losses were sitting at the bottom of the uncertainty line, it's rising, and so it's a growing problem. So you might want to prioritise this area to try and find out, is that a metering issue, or is it a growing leak in the area? So as I said before, in terms of making those intervention decisions, where that uncertainty bar sits matters. In the top example, which is just some monthly estimated losses, there's 2 very large meters in this area, 300 millimetres, and actually our recommendation is to verify those, to work out, to try and reduce the size of that big uncertainty bar so that you can actually work out whether the genuine result is sitting above that 0 line, because otherwise you might be chasing a leak that doesn't exist. In the second example, the bar is sitting above 0 and it's growing. And in this case, we'd actually say, well, we think there's a problem or something going on in the network that's worth going and spending some time investigating. I just wanted to highlight this example from another area. So it's just a sort of extract of an upstream area summarised, really. And we've got 2018-19 losses in the sort of left-hand number box and 2019-20 to date in the right-hand boxes. Now, this company had previously not done any balance work across their upstream network, but they obviously have DMA level leakage estimates, etc. And we happened to include doing 2 DMA tiles in this because they had quite a significant amount of upstream network that couldn't be separated. And so one of the DMA tiles, and it looks a bit messier than you'd expect from an upstream one, but there's, hundreds of customers. We've got 2018's water use. Unsurprisingly, big spike. It was hot, it was dry, everyone had their paddling pools out. Came back down during the winter, and then they saw a similar pattern in 2019. They went, 2019 was not as warm and beautifully sunny. So this company had been sending out resource to this DMA to look for leakage ever since they spotted this rising pattern. No knowledge of what was going on in the upstream network. So we came along and produced an upstream balance for it. And unsurprisingly, 2019, we saw this, a massive downward scale, so it's dropping down to the negative. Now, that piece of insight led us to say, we're suspicious of this meter. We think that meter is not recording correctly. And sure enough, the water company went out, looked at the meter, and it turned out it had, it was drifting. The performance was changing. I don't know the cause of that, but they have now rectified the situation, brought down their DMA leakage, causing much cheering amongst them because it was quite a significant volume. And actually, they can accurately work out now what that DMA leakage is. But they'd spent 4 months chasing mythical leaks in a DMA, crews out sweeping, looking for leaks, because they hadn't got that kind of other side of the meter issue. And this is why I think upstream stuff is so important, because what's the point of chasing leaks in DMAs if there's actually problems either at the meters or upstream? And you wouldn't know just by looking at the DMA flow. And I think my sort of final bit before I hand over to Ant, who talks a bit more about doing practical surveys, is that you can actually combine then all of these smaller areas together. And again, you then remove uncertainty, because obviously if you get more meters that become interstitial, so you can kind of ignore the performance of that particular meter, and you end up with a larger kind of area zone. You can also often see compensatory effects. So for instance, this TDMA here has a positive, but this service reservoir here has a negative. Actually, probably it's the meter or uncertainty there that's causing the issue. So they cancel each other out. So if you put them in the right order, you can see which of them cancel out and which of them actually genuinely might have a leakage problem to get you your total at the end. Oh, yes, so this is the segue really to ants. This is a final example from another water company where we'd done a tile balance and thought there was about 2 megalitres a day of leakage in an area. So the company in this case was Welsh Water, who went out. They confirmed that the meter flows were correct, the data we were using was correct, and subsequently asked our infrastructure team to actually go and survey in the area to try and find the source of this potential leakage. So inspection by our team identified the location, Welsh Water repaired it, and as you can see, this is a before-after, red and green. They did reduce by almost 2 mLD, and importantly, that uncertainty bar is now crossing 0. So the remaining bit could be just as a result of the meter accuracy. So that's my segue really to Ant and his inspection stuff. Oh yes, sorry. Yeah.
Sure you get that one. Okay, thank you, Carmen. Good morning, everybody. So yes, you've heard Carmen talking about the metering side, so identifying where potential losses may be. And I'm going to talk a bit more about the sort of practical side of things, where we've actually been out and doing surveys and what we actually find in practice. I think it's fair to say that for many years trunk mains have not been seen as a problem for leakage, and I guess that's partly down to the fact that they are large, strong structures. Typically, they if they're going to fail, they'll fail catastrophically, but thankfully that's quite rare. So people in essence believe that we don't see leakage from them. People do walk lines. Traditionally, that was the way really of finding leaks in trunk mains, walking along the ground, spotting the damp patches or the green grass in the summer, and identifying where leakage is. But what we found is that actually leaks can occur quite often at joints, and I'll come to that, in these large pipes. So the pipes themselves don't fail, it's the joints that are failing, and it's the joints that are leaking and resulting in quite significant losses actually from trunk mains. But because the pipes are strong, they don't fail catastrophically, so you tend not to pick them up as being a particular problem. So there's really 3 technologies I think are probably the most applicable to detecting and locating leaks in trunk mains. The correlator, which we heard about from Joe earlier, obviously developed, I think actually I would say it was in the 70s that WRC were working on it. Malcolm can probably back me up on this one, because I think it was, sorry, but possibly just with knowledge rather than actual genuine, with actual being there at the time. But the correlator has traditionally been used on the small networks, small diameter networks, very good on metallic and smaller pipes, and has in the past had struggled on large diameter pipes just because of the physics of the way the sound travels. Just for those who don't perhaps know how they work, but basically if you look there, you have a leak between the sensors that you've attached to the pipe. The sound travels along the pipe, and you pick it up at remote locations, and by measuring the time delay in the sound arriving at the 2 locations, you can calculate the location of the leak between those 2 points. But it does rely on the sound travelling down the pipe, and as I mentioned, the physics means that that in larger pipes the sound is attenuated quite quickly as you move away from the leak, so it can be quite hard to hear certainly smaller leaks, and in non-metallic pipes or plastics, the sound is dissipated more quickly as well. Next technique I'm going to have a look at is Sahara, bottom left there. That's an in-pipe acoustic leak detection tool. So that's a sensor on a cable moving through the pipe and picking up the sound as it goes. And finally, we'll have a quick look at Smart Ball, which is similar acoustic detection, but it's a free swimming device, so it rolls through the pipeline over long distances, collecting data as it goes. you download the data at the end and analyze it to find the location of leaks. So I just got ahead of myself slightly there on the correlator. So this just explains it in a little bit more detail. So you can see you have your leak in the center here. That's the one I have to avoid. The sensors located on existing fittings, hydrants, valves, whatever it might be, on the pipe at either end, and the sound travels along the pipe. You carry out correlation, so that's where it gets its name from, which is just comparing the two signals in time and looking for the time delay between the two signals, and that allows you to calculate where the leak is. Improvements in correlator technology means that it's now becoming more widely used on trunk mains, more successful, finding leaks over longer distances and slightly smaller sizes. So it is a technique. The thing to be wary of, though, is obviously if you start looking at very long lengths, while you might get a result which says, I can't find any leaks, it might be because it can't hear the leaks, not because there are no leaks there. So it's just worth bearing in mind these factors when you're looking at different techniques that you might apply. The Sahara system was actually developed again by WRC, so the correlator was initial research was done at WRC, I think, as I say, in the 70s. Sahara we looked at in the early 90s, started developing it in the early 90s, and that was as a direct result of awareness of the limitations of correlation in big pipe. So we decided that, yes, if you could put a sensor in the pipe, have it travel along, you were going to go past any leaks that were there, and you're going to be able to detect them. We've coupled that with a locating device so that now if you detect the leak with the sensor, the operator at the vehicle is able to stop the cable, position the sensor at the leak, and use the locating device then to pinpoint the sensor, which if it's sitting directly over the leak, they can put a mark on the ground and identify exactly where that leak is. And this is something we've actually been using for over 20 years now, particularly with Thames Water, and I'll come on to some results that we've got from that system shortly. The operator gets a number of different displays, but primarily what we're looking at there is the sound signature. So you can see as you move along the pipe, so from left to right, that's moving along the pipe. We see a peak in the absolute level, but also we're seeing a change in the leak noise characteristics. So we're seeing higher frequencies occurring, which is represented by the bottom edge of the graph, and the low frequencies are actually also building up. Helps us, that data helps us pinpoint precisely when the sensor is sitting at the leak. We've also developed the sensors for Sahara, and we have a sensor which can be used on plastic pipe. Although we can use the acoustic method perfectly well, we find that actually you can use an electrical conductivity method to find leaks in plastic pipes, and that'll also pick up then metallic fittings, so it can tell you whether your leak is at an air valve or at a previous repair potentially. So it's additional information that you might get from carrying out that survey. What we're seeing there is results from inspecting a 950 metre long pipeline, and you can see peaks which correspond to, they're actually metallic fittings on the pipeline. Slight difference in the two signal levels here because we've got some new PE pipe which has a slightly different characteristic signal to PVC pipe. But very clear, that graph was literally drawn out as the survey was carried out, so no post-processing on that at all. It gives you very precise information. You can actually zoom in on those peaks and measure how long the fitting is that was used to make that repair. SmartBall is a free-swimming acoustic device, so that logs acoustic data on board. It can be introduced into the network at an air valve location, for example, and extracted downstream some many kilometers away using a capture device. It rolls along the bottom, collecting data as it goes, so the data is time-stamped. So we need to know where we are at specific times during the survey. So monitors would be put on the pipe to monitor passage of the ball past particular points in the network, and that helps improve the accuracy of the results that are recorded. So there's tracking technology in there, tracing technology. It has a gyroscope to help map out the route it's taken. And as a result of that data, you download it, compare the position data and the time-stamped acoustic data, and that'll allow you to pinpoint the locations of leaks. And both Sahara and SmartBall, because they are traveling, they're traveling along the pipe and going right past the leak, they're never going to be more than one pipe diameter away from any leaks that might be there. So that makes them particularly sensitive to leaks. So we're able to find virtually, well, we believe all leaks that are occurring in pipes. I'm going to skip past that SmartBall one. It's an animation of the technique. If anybody's really keen, I can talk to them about that later. What I really wanted to get to, though, was the sort of results. So, what is the problem with trunk mains leakage? Well, with Sahara, over the last 20 years, we've surveyed, 2,875 kilometres of cast iron pipe. That includes resurveys, and our biggest customer, Thames, we actually sweep round their network once a year and are repeating surveys. But in that period, we found 3,400 leaks. If you just look at what the average distance between leaks is, that's 842 metres. And bearing in mind that we've been through the network, they've repaired, they don't repair all of them, they will leave the very small leaks which are probably not economic to repair and monitor them. But what we're seeing is leakage occurring at around every 840 metres, we're finding a leak. And the average size of those leaks, because we're able to give an indication of size, is around 0.15 MLD, or about between 5 and 6 cubic metres an hour. So I think you'd agree there appears to be a problem there. If we look at cast iron, so just the first survey at each site, clearly the figures are likely to be worse, because these are probably pipes that haven't been looked at. Well, they've probably been in the ground up to 158 or 180 years, some of them. So the first time we've surveyed, the first survey total is about 546 kilometres. The average distance between leaks is around the 500 metre mark, and that has been consistent over the years. And when we look at cast iron pipes, both in the UK and wherever else we've surveyed them, and also other pipes with lead run joints, so that might be concrete pipes that we've seen overseas, some steel pipes as well, we find a very similar figure of around one leak every 500 metres. Steel pipes, we've surveyed less, fewer leaks, but again, look at that figure. It's not that different. Interesting, I believe, the number of leaks that there are out there, and as I say, the average size is around 5 cubic metres an hour, and that's we've worked with water companies to look at. We assess a size band when we detect the leak, and then ask the water company to verify that when they repair it. At concrete, I mean, clearly concrete is far fewer concrete pipes in the UK. Those figures are mostly from Morocco and Portugal, in fact. Slightly better performance there, slightly newer pipes. Okay, thank you very much. I'm sure Carmen and I will both take questions now.
Mostly a question for Carmen. Thanks for your presentation. Agree with a lot of what you said. One question I had really was, as you mentioned early on, a lot of the water companies aren't seeing trunk mains as a big problem. And when you do this kind of analysis, it highlights that there is more leakage out there than we currently think. How can we go about convincing the water companies of this and to do the kinds of analysis that you're talking about?
So I think it is changing. We first started trying to do this with some companies about 6 years ago, and they were kind of a bit different. as I say, we're currently working with 3 companies and talking to more. I think the consistent measures report has helped, and also a 15% target of reduction helps, because people want to really spend their money most wisely, and actually it might be cheaper to find some leaks on the upstream network. I think it is important to say it doesn't necessarily increase the total leakage by actually understanding how much is occurring in the upstream, because you might be reducing it off the DMAs. So it's just a case of actually understanding where the problems exist. And similarly to, I think later this afternoon, we're talking about, is it a supply pipe, is it a internal wastage in a customer's property? If we actually understand, is it PCC, is it a leak, we can do something about it. We can put in place the right policies and processes to fix it. So I think the tide is turning, and often just giving it a go in a small area shows how valuable it can be.
I'm interested to know where the original belief came from within these water companies that trunk mains are not a problem, because I have heard it a lot of times, both in the UK and overseas.
Yeah, I'm too young to answer that. Here you go.
I think it is just genuinely that there's not the anecdotal evidence probably that that they're a problem. That, as I mentioned, they tend not to fail. And leakage, very often we find leaks, and the water is just disappearing into the backfill and running away. We've found leaks of the order of 5 megalitres a day. You know, that's frankly a burst almost. And there has been no evidence above ground of that occurring. And that's not just an isolated case. We have found several of that size, where, in fact, in one case, the water was coming out of the pipe and going into a sewer, an adjacent sewer. But in other areas where it just runs into the ground and is lost. And I think it's the fact that it just doesn't appear at the surface necessarily that causes a problem. And it may be that they're distributed so widely that actually they're not, as a percentage, it's not a huge volume. That's a percentage of the total volume passing down the main. At an absolute level, it's important, but as a percentage of the total volume, can be relatively small.
So obviously again, Trenchless. Do any of the methods tell you anything about the likelihood of the leak turning into eruptive burst?
Sadly not. I mean, we are detecting the condition of the size of the leak as it stands. So yeah, we're pleased to say that we're able to at least give you an indication of the size, so that should be helpful. And then if you can indicate whether it's at a joint or whether it's in the barrel of the pipe, I mean, clearly if it's in the barrel of the pipe, act now. If it's at a joint and it's small, you know, certainly in a lead run joint, then typically we would advise, you know, monitor it perhaps, particularly depending on where it is. If it's in the middle of a field, okay, perhaps you want to go and mend it. But if it's in a very difficult area, you might just want to monitor it. Oh, sorry.
University of Birmingham. I just have a question about the last slide that you showed us about the pipes. So, does that give any indication about the types of the pipe for the leakage, or it's about the age of the pipes? So, is this concrete is the best option, like we would like to prevent the leakage? Or?
No, I'm not sure that that's necessary. I mean, what you'll notice, obviously, there's no ductile iron showing. I think it is actually maybe on maybe was on the bottom, but clearly ductile iron would show up as well. It actually shows up quite poorly because the ductile iron inspections we've done have been specifically to go and find a leak that's known about on a pressure test of a new pipeline very often, rather than just a random leakage detection. So ductile iron would look good, but might look poor, but actually its performance generally would be better. The cast iron is virtually a random sample, but it is heavily biased towards work in London. Freely admit that. But where we have got data from other areas around the world, it's been shown to be sort of similar. And the concrete, that actually includes a lot of resurveys where there have been repairs done in the meantime. So it is a slightly skewed number. I think it is quite skewed actually. I think if I'd gone through and done the the first surveys for the concrete, it would look worse than it does. So I wouldn't read too much into the sort of lower numbers. I think what I'm saying is we've got a lot of cast iron in the network. I'd be out there looking at it.